Well, hello everyone. After such a long while, I'm uploading some topics in organic chemistry. Of course, we're doing organic chemistry. This is OCR, remember OCR board, and I'm starting with some topics in module 4. So basically, this one is a very quick introduction to organic chemistry and as to why it is so important. There are 118 elements in the periodic table. Of the 118, one of them is carbon. And this element on its own produces more compounds, or there are more carbon-based compounds than the compounds of all the other 117 elements put together, maybe multiplied by a factor as well. So what's so special about carbon? You see, carbon forms single bonds. It forms carbon-carbon double bonds in alkenes. In alkanes, carbon-carbon single bonds. In alkenes, double bonds. In alkynes, triple bonds. It forms cyclic compounds, like for example cyclopentane, which is alicyclic. It forms aromatic-based compounds, in which the molecule benzene, which we shall discuss in module 6.1, is based. And you see, and then in each of them there are thousands upon thousands of different compounds. So for example, alkanes, which are saturated hydrocarbons, I strongly suggest that you, I never use the word memorize in my lessons, because I want you to learn chemistry by rationalization rather than memorizing. You learn chemistry when you learn it well, when you learn it in depth. Don't forget that. Yes, I mean even alkanes on their own. If you learn the first 10 members of the alkane family, from methane all the way to decane, it is very important. Why? Because, for example, if you have one carbon, which if you remember from your GCSE is methane, right? Methane. Then if it is one carbon compound, which is an alcohol, CH3OH, it's methanol. If it is CH3Cl, it's chloromethane. If it is COOH, is methanoic acid. All the time, meth is mentioned. So, for example, for ethane, CH3, then you have ethanol, CH3CH2OH. Ethanoic acid, which is the same as acetic acid or vinegar, CH3COOH. Ether, all the time F. So if you learn the first 10 members, methane, ethane, propane, butane, pentane, hexane, heptane, octane, nonane, and decane. Some of them are, you already know, methane and ethane are natural gases, and propane and butane are petroleum gases, and then you come to octane, which is petrol, and then longer chain hydrocarbons, diesel, jet fuel, this and the other. So at GCSE, basically, you might have come across all of these things before, but then at A-level, other functional groups are introduced. So, for example, carboxylic functional group, you knew what R means. Whatever else is sitting there, we don't care. The functional group is carboxylic. Here, the functional group is aldehyde. So, for example, if you have CH3COH, it is ethanal. They end up with Al. Al. All is alcohol, al is aldehyde. Or if, for example, you have a C in the middle followed by two functional groups, neither of which are hydrogens, then that is an example of a ketone. So you become acquainted with different functional groups, names on the tin. Functional groups gives molecules their functionality, their property. So for example, if you're a carboxylic acid, is because you produce or release hydrogen ions, so you've got acidic nature about you. I'm very quickly going to go and mention some other things, like I think it is at this stage important for you to acquaint yourself with different ways we write chemical formula. Molecular formula. So for example, we write it as C2 H6, for example, right? Structural formula, then it's a little bit clearer, CH3, CH3. Displayed formula, then you display exactly where the elements are sitting. Like for example, you have this situation. And then after display formula, you come to 3D formula. So every single carbon atom, imagine you've got one straight line at 12 o'clock, another around about say 7. This shaded is coming towards you and dotted is going away from you. So hydrogen, 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 hydrogen. But then if this was methane, but since I've given you example, giving you ethane as an example, then you write that, and then maybe you've got again 2 straight line, 1 dotted and 1 shaded, and that is 3D structure. With 3D, each of these formulas have their own usage. Usually you write that when you just want to, for example, show how, let me write that a little bit clearer, C2H6. When you don't care where the elements are sitting. For example, if you're burning C2H6, you know 2 carbons burn, produce 2 carbon dioxide, and 6 hydrogens produce 3 water. But here, in structural formula, they are much clearer as to where the hydrogens and carbons are sitting. In displayed formula, we usually use displayed formula when we want to show how a chemical reaction takes place, and showing reaction mechanisms, for example, how bonds are broken, new bonds are formed, we use that one. 3D structure is the real thing. These molecules have 3D structures. For convenience, we write them on 2-dimensional paper, right? Or we write them differently. But in reality, all molecules have a 3D structure, and sometimes examiners want to know if you know what the actual structure looks like. But usually they are not essential for our purpose. You do not certainly write 3D structure if you want to balance a chemical equation. Empirical formula. In empirical formula, you need to know if that formula is divisible by any number. Obviously, that's divisible by 2. So the empirical formula for ethane becomes CH3. So what is the use of this? Well, it is quite useful, because what it tells you is that I have a compound in front of me that comprises of only carbon and hydrogen, and in that ratio, for every 1 carbon there are 3 hydrogens. So that is pretty useful. And one thing that I think in more advanced courses, and when people really know their chemistry and they don't want to waste time drawing formulas like this, is the skeletal formula, which is for skeletal formula for ethane, it is that. As soon as you put pen to paper, that's your first carbon, right? And if you extend it, that's the second carbon. So that's propane, that's butane, that's pentane. Now imagine trying to write that as CH3, CH2, CH2, it's going to take forever. So if you know what we're talking about, that's what we do. We write them in skeletal formula. Certainly most of the questions or the topics definitely in organic synthesis that I discuss with my students in year 13s is skeletal formula. And a lot of questions on your exam papers, the structures are actually written in skeletal formula. You do not write hydrogens, you do not show hydrogens, you do not show carbon. But should you have another functional group, for example, then you show that. So this is chloroethane, right? So this is propane. This is 2-chloropropane. This is 2,2-dichloropropane. Is it making sense? Because the longest chain is a propane. You've got 2 chlorine molecules, or 2 chlorine atoms sitting on it. Where are they sitting? What are they? Chlorine. Where are they sitting? On the second carbon. What about the second one? Is it the second one sitting on the second carbon atom? Yes. So it is 2,2-dichloro, in this case, propane. But what about if you had 1 chlorine sitting there and 1 chlorine sitting there? So in that case, it would be 1,2-dichloropropane, right? So when you write the actual formula, the C3, it would have been CH, but it is now H6Cl2. If somebody gave you that, which one do you think is the actual structure? If I ask you to go and fetch me a dichloropropane, which bottle are you going to pick up? Well, unless I tell you whether it is 2,2 or 1,2 or 1,3, well, or 1,1, you wouldn't know, would you? So it is absolutely essential to name organic compounds appropriately and properly. So this is something that I'm going to ease into straight away. So this is propene, isn't it? And this is 2-iodopropene. You've got a double bond. I mean, if you've got a longer molecule like that, and you've got a double bond over there, so this is an alkene. If you come from this end, the double bond is between number 2 and number 3, right? So it is 1, 2, 3, 4, 5, 6. So it's a hexene, but it is a hex-2-ene. Because you get to the double bond the quickest going this way, not going that way, right? Because it would be 1, 2, 3, 4. It would be hex-4-ene. You're not going to name it hex-4-ene if you can name it hex-2-ene, do you? Because 2 is a smaller number. So hex-2-ene, what I call is the mother molecule, right? But what about if it's got other things sticking from it? So for example, if it's got iodine sticking from there and a methyl sticking from there. Remember, for methyl, we do not write carbon or hydrogen. So that line means there's a methyl there. How do we name this? Well, whatever other things are attached to your molecule, you have to go by alphabetical order. Of course, I in the alphabetical order comes before M for methyl. So with respect to that being number 2 carbon, this is number 3 carbon, so that would be number 4. So you have to write 4-iodo. For halogens, you write fluoro, chloro, bromo, iodo. So 4-iodo, and then the methyl is sitting on the 5th carbon, isn't it? 5-methyl. Then, of course, you write hex-2-ene. Hex-2-ene. Unless you name it correctly, people don't know what you're talking about. I always tell my students, it's like you're sending a parcel to a country, so you get the country right, you get the city right, you get the road right. But if you don't get the road, the door number right, the parcel will not be delivered, or cannot be possibly delivered. Everything about the naming compounds should be correct and spot on. Usually you get 1 mark if it is not too silly. I think, as a question, I think this is just about okay, this example over here, for 1 mark on your A2 paper. So this is naming. For alcohols, of course, all. So 1, 2, 3, 4, 5. So this is pentanol, but it is pentan. Which one? 2-ol. We count it from that side. Yeah, you remember molecules are moving in space. You know, if all is sitting over here, this is still the same molecule, isn't it? Even if you turn it right, you know, the other way around, upside down, this way and the other way. So this is pentan 2-ol. Some of you are that do biology. You have come across this, haven't you? Do you recognize this? Well, those of you who recognize this, you probably recognize it as glycerol, which is a generic name. It's not a real name. It's just given them a name. Glycerol. But this is propan triol, isn't it? But then, where are the alcohol functional groups? Oh, one of them is sitting on carbon number 1, one on number 2, one on number 3. So you have to say so. So it is propan 1, 2, 3 triol. Makes sense, doesn't it? When you think about it. Tri, because there's 3 of them. If there were 2 of them, it would be diol. You see, all 3 OHs could have sat over here. So in that case, it would have been propan 1, 1, 1 triol. Which it isn't. It is that. All right? Now, speaking of alcohols, let me just mention something else as an introduction before I wrap this up. Another idea. So all these examples I've told you, for example, you've got propan 2-ol or propan 1-ol. They both have the same chemical formula, don't they? But they have different structural arrangements. They are each other's isomers because they have different structural arrangements, yeah? Different structural arrangements. Now, when you think about it, if for example you have octane, 1, 2, 3, 4, 5, 6, 7, 8. So that's octane, C8H18. If you take 1 carbon off, then it would be heptane, isn't it? And then you put that carbon you've taken off somewhere else, like here. How would you name that? 2-methyl heptane. If you take that off from there and put it here, 3-methyl heptane. If you take it off from there and put it here, 4-methyl heptane. So you've got 4 different heptanes, but not heptane. There's a methyl sticking out from somewhere. And you can imagine, and after you have exhausted all the heptanes, which with this third example they are exhausted, because if you now put it over here, it would be 3-methyl heptane again. You count it from the other side, right? Then you can take another carbon and then you can put that on the hexanes from now on. And therefore, and then you can imagine for the same chemical formula, sometimes we can have many tens of different structural isomers. And so no wonder, and this is just one compound from hundreds, perhaps thousands, perhaps millions of organic compounds. And each of them exhibit different isomeric structures. And therefore no wonder the whole of organic chemistry is so extensive and massive. Just one thing before I stop this video is that let's say this is pentan 1-ol. this is pentan 2-ol. I beg your pardon, this is 3-ol. This is 2-ol. And then this is pentan 3-ol. Agreed? Now, this is a primary alcohol. Primary, one with a tiny little circle on top, like degrees Celsius circle. Primary alcohol. Why? Because the functional group is attached to a carbon, this one, which is attached to just one other carbon atom. Or is attached to a carbon which carries 2 hydrogens. This one, the functional group is attached to a carbon which is attached to 2 other carbon atoms. Yeah? And this one also is, and therefore that makes it a secondary, and that makes it a secondary. But what about this one? In this one, yeah, so you have 1, 2, 3, 4, 1, 2, 3, let's put another one there. So you have your functional group which is attached to a carbon which is attached to 1, 2, 3 other carbon atoms, and that is a tertiary alcohol, right? Tertiary alcohol. Why is it important to know whether your alcohol is primary, secondary or tertiary, or what structures they have? Because their chemistry is different to one another. For example, when we oxidize them, we'll do other things that I will discuss with you in the next lesson. Right? So to reiterate, let's go back to these pages that we have done together. We started with organic chemistry. We started to actually discuss why this subject is so enormously important. So as far as the industrial chemistry is concerned, it's all of these, but all protein molecules, amino acids, fat molecules, sugar molecules, starch molecules, us. We are all carbon-based. Sugar in us, starch in plants, proteins we make, amino acids, fat, they're all carbon-based. And then in the industrial world, in the chemical industrial world, again, millions of each of these guys make all these medicines and all these drugs that we're using from everywhere that you look, from polymer industry to pharmaceuticals, fine chemicals. Just look around you and see how many different synthetic materials you see that has actually engulfed us. Everything, everywhere, from chairs you sit on to floors you walk on, from the shoes you wear, from the clothes you wear, most of them are synthetic materials. But then not just the industrial side, but also from proteins that are made from amino acids, amine on one side, carboxylic on the other side, carbon in the middle, to fat molecules, to sugar molecules, to all carbon-based. Okay, so we will, next time that we'll discuss things, we'll discuss delve into the reactions of, say, for example, alcohols, and we'll take it from there. Okay? Well, thank you very much.